So today we're going to finish discussing about electroweak baryogenesis and some of the theoretical issues. And I had asked people to try to come up with some questions. So hopefully by the end of our first lecture today, I'll get some good questions from everybody. So let me share my screen and let's do this. And we will start the PowerPoint here. All right. Okay, that's odd. Huh. Well, my screen just went blank. I'm sorry about this. I don't know what happened. There we go. Oh, PowerPoint quit on me. Let's cancel that. Sorry about that. Let's try this again. Okay, let's now do the slideshow. There we go. Hopefully everybody sees this time. So today, the first topic that I want to discuss in more detail is critically important to the viability of electroweak baryogenesis, which is the topic of electroweak sphalerons. So what I would like to do for you is put the sphaleron rate, which we alluded to a few lectures ago, in the context of electroweak baryogenesis. And then I'm going to show you how we can think of the sphalerons in terms of topology and how this motivates the form for the solution, as well as the computation of the sphaleron energy. Excuse me. And the sphaleron energy is a critical input to the rate. And then I'm going to discuss some of the theoretical issues that one encounters in computing the sphaleron rate in perturbation theory, and some of the pitfalls that have appeared in the literature historically that you should be aware of if you are going to get involved in this research at all. And then I'll spend a few minutes at the end just talking about what is the state of the art with doing calculations of sphaleron properties non-perturbatively. And hopefully this will lead to some questions. So here's the outline. We'll first talk about the connection between sphalerons and the problem of preserving the baryon asymmetry inside the broken phase after the electroweak phase transition. Then the discussion of sphalerons and topology, the calculation of the sphaleron rate, and finally a brief bit about the non-perturbative calculation. And there are several references that I put here for you. And so again, I leave these for you for your further reading if you are so interested. So let's start with the problem of preserving the baryon asymmetry inside the broken phase and creating it outside. And let's remind ourselves the basic setup of the sphaleron dynamics. So the sphalerons, as I said, are a configuration of the gauge, and it turns out the Higgs field in the SU2 in the standard model, a solution to the classical equations that is a saddle point in the energy surface, and we'll come back to that shortly. And because of the electroweak anomaly, the transition from one minimum to the other in the energy surface through a sphaleron corresponds to a change in the total baryon plus lepton number, which is proportional to the number of families of fermions. So the cartoon that I gave you before was the one on the right, which shows a sphaleron eating up a total B plus L of 3 units, one for each family of standard model fermions. So what the sphalerons do is they convert a left-handed chiral charge density to the baryon asymmetry, and they also wash out the baryon asymmetry. So there are both our friend and our foe. Let me remind you also about the anomaly, why the sphaleron is somehow connected to the anomaly. This is the anomaly diagram that we discussed before, and it leads to an anomalous divergence of the baryon plus lepton number current that involves the SU2 and U1 hypercharge field strengths times their dual. And the important part is the WW dual part, as we'll remind ourselves in the next slide. So just that's the same formula. And this is somehow related to the change of the Chern-Simons number. Now, the Chern-Simons number, I defined for you before, it's an integral over antisymmetric product of 3 of the SU2 gauge fields, and it's somehow contained, as you see, inside the WW dual that lives in the top box. So because if I now integrate the first equation over all space, and if I assume spatial isotropy, then what one ends up with is a time derivative of the charge component of the current, but integrated over all space. That's just the B plus L charge. And that time derivative of the B plus L current charge is really the time derivative of, or related to the time derivative of the Chern-Simons number. So the anomaly is really telling us that there is a change in Chern-Simons number that's possible due to the configuration of the gauge fields. So that change is related to the total change in baryon plus lepton number through a simple factor proportionality, twice the number of families of standard model fermions. So how does this come in then to our actual calculation of the baryon asymmetry? Well, I've just taken the B part of B plus L. If we assume that B minus L is conserved, then we can relate the B plus L current to the B current by equating B and L. So you have in the top box here an equation for the divergence of the baryon number current, and it has inside the square bracket two terms called K1 Weeks Phaleron and K2 Weeks Phaleron. K1 Weeks Phaleron is proportional to the number density of baryons, and K2 Weeks Phaleron is proportional to the number density of left-handed fermions. In the exterior of the bubble, these rates are fast. K1 and K2 can be related to the Weeks Phaleron rate per unit volume, and there's a temperature cube factor that comes in. The K1 term is a relaxation term, meaning if I start with some baryon number that is non-zero, then that term would like to relax it to zero. And so there's a prefactor that comes in K1 Weeks Phaleron called script R, and you might think of that as for relaxation, and it has a number one can work out that's about just about 4. The second term that is proportional to the left-handed number density of fermions is the source. So if our CP violating processes during the phase transition generate a non-zero net number of left-handed fermions, then that will act as a source for the baryon number current. And if you remember yesterday, we had that example of solving the transport equations to get the left-handed number density as a function of distance from the bubble wall. It's really that term that is generating the baryon asymmetry, but then there's a kind of back reaction that likes to relax it to zero outside the bubble. Now, the size of the Weeks Phaleron rate per temperature cube per unit volume outside the bubble is proportional to temperature, and it turns out parametrically it goes like the 5th power of the fine structure constant associated with SU2 and a prefactor called kappa, which from numerical studies, non-perturbative studies, one finds is about 20. Okay, so this is the unsuppressed Phaleron rate outside the bubble. Inside the bubble, the number density of left-handed fermions is unimportant, and the rate there, it turns out, that would be a source for baryon number inside the bubble is highly suppressed. So we take K2 inside the bubble to be approximately 0, but K1 is still non-zero, and it's proportional to the Weeks Phaleron rate inside the bubble. So our real problem is to assess how large the Weeks Phaleron rate is inside the bubble, and we want to ask the question whether or not it is small enough to ensure that the baryon number that's created outside the bubble and that diffuses inside is preserved, is not washed out. And that again is a requirement that we sometimes say of a requirement for a strong first order electroweak phase transition. Sufficiently strong means the Phaleron rate inside the bubble here is suppressed sufficiently. So how does this then translate into a baryon number preservation criteria on the theory? Well, one way to encode that is to work with something called a washout factor. So the washout factor I'm going to call S, and it's given by a ratio of two baryon number densities. I use rho in this case rather than N. The numerator is the baryon asymmetry after the electroweak phase transition completes. It is, so delta T electroweak is the duration of the phase transition. The denominator is the initial baryon asymmetry that's created right when the nucleation process is starting, when the transition is starting. And that's all a function of the CP violating dynamics that we discussed a little bit yesterday. Now, there's going to be some requirement that the final asymmetry compared to the initial asymmetry is not too small. It has to be larger than some number. And just for convenience, I wrote that number as an exponential of minus n. And what that number is really depends on how large the initial baryon asymmetry is. So for example, if the initial baryon asymmetry were 10 times the observed baryon asymmetry, then e to the minus n could be 1/10 and still allow us to have the observed baryon asymmetry by the end of the transition. But if it was smaller than 10, then the requirement on the right-hand side, of course, would be larger, right? You couldn't wash out as much baryon asymmetry. So it really depends a bit on your assumption about how well the CP violation is effective in the initial phases of the transition. So when we solve the equation for baryon number, then it turns out that the log of this washout factor has the following form. It's proportional to a prefactor called A, which is a function of the temperature, and we're going to take that to be the critical temperature of the transition. And then there's an exponential factor where the exponent comes with a minus sign is the Sphaleron energy over the temperature at the transition temperature. So we have that the larger the Sphaleron energy, the smaller the, I got this sign wrong. It's got to be a plus sign. I'm so sorry about that. This should be plus. So I'll have to send updated notes here. So the larger the Sphaleron energy compared to temperature, the larger the exponential factor and the less likely you are to wash out the baryon asymmetry. Okay. So there are two quantities that are important here for us. One is the critical temperature, which we get from studying the evolution of the effective potential, and the other is the Sphaleron energy, which, as we will see, comes from studying the effective action, or the generating functional from which we get the effective action. So the theory challenges are the following. The first is to compute the washout factor consistently in perturbation theory in order to apply to various models of interest. And the quantities of interest, as I said, are the critical temperature, the Sphaleron energy, and it turns out, as I'll show you later, there are quantum corrections to the classical solutions. And the second important challenge, which is really still in its early days, is to assess the reliability of perturbation theory calculations. And the best way to do that is to use lattice simulations. And I'll allude to this a little bit at the end of this lecture. So I now, with that as the context, and I want to talk about the form of the Sphaleron field configurations, the solution, and how that can be extracted from arguments based on topology, and then used to compute the Sphaleron energy. And again, let me just remind you that in terms of a picture in field space, the Sphaleron is a static saddle point solution to the classical field equations. And what we're going to see is that topologically, these correspond to what are called non-contractible loops. And loops are going to be defined in a way that we'll discuss. And the really fundamental papers on this topic are the two that I've listed here. And today I'm mostly going to follow the first paper by Manton, which is discussing an SU2 Higgs theory. And that was, by the way, at 0 temperature. So here's the starting point. And the starting point is to make an analogy with a torus. So here's a picture of a torus or a donut on the left. and it's tipped on its side. And so that one can then talk about the height of the point on the torus from the plane on which it rests. So we'll call the height a height function. And it turns out that the torus has 4 extrema. The height function has 4 extrema. It has a maximum at P3. It has a minimum at P0. And then at P1 and P2 are what are called saddle points, which are minima in one direction and maxima in another as you move along the torus. So one can then define a set of what are called non-contractible loops by starting at the point P0, the minimum point, and drawing something that goes around the torus and ends back at the point P0. And there's no way that you can shrink that loop to a single point because of the topology of the torus. Okay, so that's what you mean by, sort of intuitively mean by non-contractible loop. Okay. I don't know why I didn't list that originally. So what we're going to do is we're going to parameterize the motion along the loop by a quantity I'm going to generically refer to as mu. And you could just think of it as maybe a displacement along the loop or some other parameter that characterizes how far we are along any given loop, okay? And we're going to then make an analogy between this picture and the topology in field space. So if we go to field space, let's work with the SU2 left Higgs theory, which for the moment will neglect the U1 hypercharge. And what we want to look for are the static solutions to the equations of motion, the field equations for the Higgs and the gauge fields. And it turns out to do that, it is convenient to fix the gauge. So I'm going to define the components of the gauge field by taking the zeroth component is going to be 0. And then we're going to take A dot dx to define a radial, a polar angle component, and an azimuthal angle component. And the gauge choice we're going to make is that the radial component is 0. And then what we're going to do with the gauge being fixed is define a map that will allow us to talk about a loop by using the behavior of the fields at large radii. These are called asymptotic field conditions. Now, before doing that, I need to define some notation. So let's call phi t, this is just the transpose, as the Higgs doublet. It's got the 2 components, and it is sometimes convenient to write it in terms of a purely real set of fields. So the real and imaginary parts of phi 1 and the real and imaginary parts of phi 2. And we'll use that notation going forward. But occasionally we'll also use the 2-component complex doublet notation. And of course, the vacuum that we live in today at 0 temperature is given by 0 in the first component and the Higgs vev, v over the square root of 2 in the second component. That's our normalization. Now, this 4-component notation defines a space called S4 that has certain properties that we won't go into. And we're going to work with that shortly. And what we're going to first do is look at the behavior of the field at asymptotic and asymptopia at r goes to infinity. And we're going to define what's called a vacuum manifold for these asymptotic fields by requiring that at r goes to infinity, the magnitude of phi is the Higgs vev over the square root of 2. Now, pictorially, we can think of it in the following way. We're working initially in 4 dimensions, S4, and the manifold, the condition that phi is v over square root of 2 restricts us to a subspace, S3. But if you want to have a picture in mind, you can think of taking ordinary O3 and restricting it to a sphere, which is a subspace, okay, of O3. And so we're kind of doing the analogy for our 4-component Higgs field. And we're going to define the radius of this sphere in this three-dimensional sphere in field space the radius is v over square root of 2, and we'll define one point to be the vacuum configuration. So in four-dimensional components, it's 0, 0, v over square root of 2, 0. And you can think by analogy that it's like having a particular vector pointing to a particular place on this sphere. Any other point would have the same norm, but this will be our vacuum configuration. A loop, then, will be a motion on this sphere, S3, that starts and ends where this vector is pointing. Okay, so we're going to consider all possible ways of moving around this sphere and ending back up here. That's what's going to be our analogy with the loop on the torus. Now I need to define another parameter. The way we're going to define the parameter mu that characterizes the motion along the loop is the following. So here's our sphere of magnitude v over square root of 2 in field space. And here is our vector that describes the vacuum configuration point. And I now want to draw a set of planes that cut through the sphere and all go through the point where this vector ends. And we're going to define one for reference, and then as you move another plane relative to this plane going through the same point, the angle between the two I'm going to call mu. So we can characterize any point on this sphere, it turns out, with three coordinates. Because we're in a subspace, that we're in an S3 rather than a subset of O3, then there are three coordinates needed to specify. Two of them are going to be the ordinary coordinate space azimuthal and polar angles, theta and phi. And the third is going to be this parameter mu. And the magnitude of this any point vector on this sphere has to be v over square root of 2. So this defines the sphere in S4 where we restrict to the magnitude v over square root of 2. So as I said, theta and phi have the same meaning as in R3. Mu is going to range over the angles from 0 to pi. And as you move the plane from 0 to pi, you're going to sweep over all points on the sphere in some way. And we're going to identify mu equals to 0 and mu equals to pi as the vacuum vector. So that's our requirement, that we start and end at the same point. That's like staying on the torus, we started and ended at the point P0 when we draw the loop. Okay, so this is all at large R. Now, the loop allows us, the motion on the loop, to define a map. And this is a little bit non-trivial. The idea is the following. Let's pick a point on our loop, a point where the field phi is. I'll call that point P, which is described by those vectors that lives on S3. And we're going to map that point to another point on the same sphere. And I'm going to call that result of that mapping phi tilde, that also lives on S3. So I take a point here and I map it to another point here. And as I am moving the angle mu, I can define a map any way I want. Whatever the point P is, I can define some way of identifying another point on the sphere. Okay, that's the map. Now, the simplest map that I could come up with is the identity, meaning I take a point on this sphere, and under the map, I come back to the same, I map it to identify it with the same point. And that's in fact what Manton did in his paper. So he said, let's take the simplest one. So phi tilde is going to have the same coordinates as phi. P of mu, theta, and phi. Now, what about the gauge fields? Well, the gauge fields are going to be defined in terms of a gauge transformation, SU2 gauge transformation matrix U, and we can express that particular gauge transformation matrix in terms of the asymptotic Higgs fields. And the way it's done is in this matrix form here. So the diagonal elements are the phi2 field, and the off-diagonal elements involve the phi1. Okay, so this is a 2x2 matrix complex entries. And so the gauge field, of course, is given by derivatives in theta and phi of U, and then we multiply the whole thing by U inverse. Or I could integrate by parts and take U, and I have the derivative of U inverse. And again, remember, A sub R is equal to 0. So we've now defined points on the sphere and the map, and we've done the same for phi, and we do the same. We then make an identification of what the gauge fields do. And now to specify each of the loops, so the loop, remember, is take a point and identify it with another point on the sphere and do that as a function of this mu parameter. But that doesn't specify the loops completely, because we've only talked about the behavior of the fields at R goes to infinity. So to fully specify the loop, we have to bring back the dependence of the fields on R. And the way that Manton did that was in the following. He said, let's take phi of mu, R, theta, and phi as having some coefficient of the field at infinity times, which is a function of R. And then there's another factor. To be honest, I don't fully know why this particular form was motivated. Probably figured out if I thought about it a little bit more. But it's 1 minus the same function here. And again, our formula for phi at infinity, before we wrote it in terms of the 4-component S4 vector, but it can always be rewritten in terms of the complex doublet notation, which is written down here. Similarly, for the gauge fields, Manton introduced a radial function that defines the gauge field at any radius as being this function f of r times the gauge field at the R goes to infinity asymptotic location. Well, we maintain the gauge choice that A sub R is equal to 0. So now, what Manton points out is that the maximum energy on each loop comes when we take mu equals to pi over 2. So that's a little bit like saying that as you move along this loop on the torus, the maximum energy is here, and the way we've set it up, that point for the fields corresponds to mu is equal to pi over 2. The different, okay, so that's the maximum energy. The different loops correspond to different choices of these coefficient functions h and f. The saddle point corresponds to the choice of h and f that give us the minimum energy at the maximum value, meaning at mu equals to pi over 2, what is the choice of h and f that brings us to the analog of P1, the minimum energy we can have at the maximum height or the maximum energy. So again, the height, the energy is analogous to height. Mu is telling us that we move along the loop. The different choices of h and f correspond to different loops, and the saddle point configuration is the choice of h and f that gives us the minimum of these maximum energies as we move along each loop.
Can I ask you a question?
Yes, please go ahead.
So are we using energy function as a height function?
Energy is analogous to height, yes.
So then here, what energy is this? Well,
I haven't shown you the energy functional yet. I will do that in the next slide, but what I want you to use the torus analogy for is just to have as a mental picture in mind of the energy is like the height on the torus.
Okay.
And so as we vary h and f, we're going to minimize the energy to find the H and F that give us the point P1, or the loop that goes through the point P1.
Mm-hmm. Okay, thank you.
Great, thanks. All right, so that point, again, let me remind you, is a saddle point, because in the torus analogy, as you move this way, you're increasing the height, whereas if you move back along the loop, you're decreasing the height, so it's a saddle point. And so in analogy in field space, the saddle point configuration will be, if we move up and down here, that's effectively going to larger energies by going to different loops, whereas if we move along the loop, we're changing mu away from pi over 2 and decreasing the energy. So the maximum energy on each loop is at mu equals to pi over 2. Now, to actually compute and find these functions, it turns out to be convenient to introduce some dimensionless coordinate that rescales. It's called C, and it's given by the gauge coupling, the Higgs vacuum expectation value, and the radius. And so the formula for this parameterized field at mu equals pi over 2 is very simple. It's v over square root of 2, the coefficient function, and it turns out that the value of the phi field at infinity at mu equals pi over 2 can be expressed in terms of this U matrix that I gave you before. And U can actually be written in terms of the spatial coordinates. Because we fixed the value of mu, it only depends on theta and phi. And so if I take 1 over r and I use the coordinates, x and y and z, those are functions of only theta and phi. And it turns out that's what u of pi over 2 is at r goes to infinity. So it's a really pretty formula, actually. So we're going to use that, and we're going to require that F and H minimize the energy, and I'll show you the energy functional in just a minute. But here is the set of equations that one has to solve in order to find F and H, subject to appropriate boundary conditions. And so here's the energy functional as a function of F and H. And this is the function that has to be minimized to find the saddle point configuration. So this can be done under certain assumptions analytically, but more generally numerically. And it turns out that it is convenient to write the resulting energy of the sphaleron as 4 pi times the Higgs vacuum expectation value over G. And then there's a function that is a function of, in the standard model, the Higgs self-coupling over G squared. And you can see why it's a function of that quantity, because here is lambda over G squared. So what would we do at finite temperature? Well, the simplest ansatz is to replace the 0 temperature sphaleron energy with a finite temperature solution by replacing the Higgs vacuum expectation value with an appropriate scale at finite temperature. Now, as we will see shortly, this should not be the full vacuum expectation value at finite temperature. Otherwise, we're going to introduce some theoretical ambiguities. But the idea is that everything else looks pretty much the same. The only thing that's really changing at finite temperature at this order is the one-dimensional parameter in this problem, which is V. And so let's replace it by some appropriate temperature-dependent scale. All right, so now we come to the issue of what should be this V, or V bar. Okay? And there I'm going to follow a discussion of some work I did with my former student, Haren Patel, to try to alert people in the community to some of the pitfalls that people have fallen into when they've tried to naively follow this prescription calculating the sphaleron energy. So let me again fix my sign issue here, and I'll have to send the updated slides. So here's the point. We want to get back to the washout factor and calculate this ratio of this Phaleron energy to the critical temperature. And we want to do that very carefully. And so what you will, and by the way, this ratio in general is somehow a function of the Higgs field at any temperature, okay? What you will see in the literature often is that this requirement that the washout factor be larger than some number e to the minus n translates into a requirement on the ratio of the Higgs field at the critical temperature to the critical temperature. This is known as a baryon number preservation criteria. That's what we called it, so BNPC. In order to preserve the baryonic symmetry, how large does phi over T have to be at the critical temperature? Now that's the conventional expression, and I'm going to tell you that it's wrong. At least it's dangerous because of theoretical ambiguities. So the theoretical ambiguities are the following. The first is that the naive way of calculating this ratio is not gauge invariant in much of the literature. And so what one has to do is be careful to implement gauge invariance. We already discussed, as you may recall, the issue of gauge dependence in the effective potential from which one derives the value of the critical temperature. Well, it's even more fraught when you are now trying to find the value of the field that minimizes the energy at finite temperature. And so one should also remember, by the way, that a field itself is not a gauge invariant quantity. So it's really quite fraught, and we'll discuss that a little bit. There are other issues that come into calculating this requirement. One has to do with something called the fluctuation determinant, which I'll explain briefly. An assumption about the duration of the electric phase transition, and more generally, just how valid is it to do this in perturbation theory. And let's go to the gauge dependence issue first. This was actually not us who realized this, but actually in some of the earlier literature, even in the standard model, people realized that there was, in perturbation theory, a gauge dependence problem, but it was never really carefully thought about except in one case, which I'm going to tell you about. So the ways to address the gauge invariance problem are the following. For the critical temperature, what Haren and I pointed out is that you could obtain it using an H-bar expansion of the effective potential. Or there are other ways to get a gauge invariant critical temperature, such as a Hamiltonian formulation and so forth. So that's a whole topic in and of itself, as I said yesterday, so I'm not going to spend a lot of time on it, but for the denominator that comes into the ratio of C, there is a well-defined procedure for getting TC. For the energy scale that goes in the numerator, one has to find an appropriate energy scale that's gauge invariant. And that's something that was actually done in the early literature, but then people forgot about it. And I'll show you how they forgot about it. So let's now spend a little time deriving the actual baryon number preservation criteria, which will lead to a somewhat more complicated formula than what you just saw. Our starting point is this washout factor, which we want to compute. And we compute it by solving the equation for the rate of change of baryon number density inside the bubbles, the broken phase. Remember, there's no source, so there's just a relaxation. So rho b dot is minus some appropriate coefficient times rho b, and the formula I gave you before for this coefficient, which I call here v sub b, is written in terms of a numerical factor, the number of families of fermions, the Phaleron rate divided by the volume and temperature cubed. So the washout factor is then obtained by taking this number and integrating it from an initial time, the start of the transition, to the final time. And in order to do that, we have to say something more about what this Phaleron rate is. You know how time evolves, yeah? We discussed temperature evolves with time. We discussed that in the second lecture. But the Phaleron rate calculation is what we need to get the time dependence of of the sphalerón rate. So one simple approach is to assume that the rate is not varying too much over the duration of the transition. That is something that one can study. But then you would factor it out and you would do the integral. Then you evaluate it at the critical temperature and take a double logarithm to get the final expression for baryon number preservation criteria. Our goal is to evaluate the inputs in this procedure in a gauge invariant manner. So let's calculate gamma. Gamma is actually given by the following formula, and there's a picture here that's based on quantum mechanics that says that the rate for decaying out of a saddle point involves the absolute value of the curvature squared, that's omega minus here, and a ratio of the partition function for this configuration compared to the partition function or the generating functional at the minimum of energy. That's Z0. And it's the imaginary part of the saddle point configuration that one needs, because that's when you have a decay, it's the imaginary part. So again, let me remind you what Z is. Z is a functional integral over all the fields and an exponential of the Euclidean action. And Euclidean action, again, I've written here at finite temperature, we integrate up to 1 over temperature with imaginary time and overall space of the Euclidean Lagrangian. So the procedure here that was followed in the early papers, and in particular, there's work by Larry McLaren, who's now the director of the Institute for Nuclear Theory in Seattle, who did this right. What he did is he said, let's integrate out the high temperature modes. And that gives us a gauge invariant renormalization of the quadratic fields in the Lagrangian. That's a procedure known as dimensional reduction, which I will actually describe in more detail after the break. This introduces a gauge invariant scale. It only involves the phi squared term in the Lagrangian, and it turns out one can show that the coefficient of that term as a function of temperature is gauge invariant. I'll call that coefficient V bar squared, and so V bar is given, it turns out, by the 0 temperature Higgs vacuum expectation value, and this square root that involves the ratio of the temperature to the temperature T naught that we introduced in the third lecture on the effective potential at finite temperature. Okay, it would be the critical temperature for a second order phase transition. This is the quantity you should use when you do the leading order calculation of the sphalerón rate, not the full Higgs vacuum expectation value, because that, it turns out, is gauge dependent. Now, some other steps that are followed are to rescale the coordinate by V bar and assume that the 0 frequency modes, the Matsubara modes, are dominant. And so one ends up with now an expression for the Euclidean action that goes into calculating Z that is rescaled by something called the 3-dimensional effective gauge coupling. And it's given by the 4-dimensional coupling divided by V bar times beta. Now, there are quantum fluctuations, of course, because we're working with a field theory. So far, we just evaluated the saddle point, but we didn't evaluate the quantum fluctuations. So the quantum fluctuations involve what's called the fluctuation determinant, which you undoubtedly have encountered in field theory. So the full sphalerón rate involves this frequency, the negative square root of the square root of the negative curvature divided by pi. There's an imaginary part of this ratio, which I'll come to in a second, and an exponential, this is the leading order contribution to Z, of 1 over the temperature times the difference of the sphalerón energy and the vacuum energy. So what's this ratio? This ratio is the fluctuation determinant. And so the determinant, the matrix from which you take the determinant is called omega. Omega 0 is for the fluctuations around the vacuum, and omega sub sphaleron is for the fluctuations around the sphaleron configuration. And that turns out to be convenient in this ratio to divide by G3 cubed in each one. So one can be a little bit more careful about doing this. There's some subtleties in field theory that I'll just tell you about, but we won't have time to go through in detail. First is I'm going to take E0 to be 0, which I can do. And then it turns out that there are certain modes that you shouldn't include in the fluctuation determinant because they're not really quadratic fluctuations. These have to do with symmetries that remain. These are broken symmetries. These are zero modes, rather, associated with broken symmetries. So the sphaleron breaks two symmetries. It breaks rotational invariance and it breaks translational invariance. So there are modes, quantum fluctuations, that are not quadratic associated with these broken symmetries. And so we can't include them in a fluctuation determinant. Where we put them is in this prefactor here, it turns out, and we don't put them in the fluctuation determinant. One other little bit of information I'll introduce you to is there's the fluctuation determinant is sometimes called kappa, and so you'll see in the literature this kappa, and it's really this ratio of fluctuation determinant around the vacuum where the symmetries are good, so there are none of these zero modes, and then in the denominator is the sphaleron fluctuations, where the tilde means we took out the zero modes associated with broken rotational and translational invariance. So we put all this together and work through some of the details and go back to our requirement on the S factor, and we can work out a new baryon number preservation criteria, which is given by this formula here, which looks a lot different than what I showed you earlier. So let me again remind you the notation. C is just the ratio of the sphaleron energy over temperature. And again, the sphaleron energy can be written in terms of this, now this gauge invariant scale, V bar of T, times this function that we get from doing the numerical integral, which is a function of lambda over G squared. And by the way, I should have said that V bar is the Higgs vacuum expectation value if you would only keep the quadratic and the leading order quartic term in the finite temperature effective potential. In other words, if we had a second order phase transition and worked in the high temperature effective theory, V bar would be the Higgs vacuum expectation value, and that is gauge invariant, but the full expectation value is not, so we shouldn't use the full expectation value. So the criteria in this that's encoded here actually leads to a requirement on V bar over TC. So what are these different factors? Well, kappa is the fluctuation determinant, and even in the standard model, the logarithm of kappa can vary quite a bit as a function of lambda over G squared, okay? So the exact calculation in this paper by Carson, Lee, McLaren, and Wang, which is now 30 years old, believe it or not, is given by this curve here. And you can see that depending on the value of the couplings, there's quite a bit of variation in this logarithm. Okay, so be aware of that. If we were to do the calculation in a beyond the standard model context, which is what's really relevant for us, then we would need to know what the dependence of kappa is on the additional parameters. And right now we don't, actually. The next term is a logarithm of the ratio of the duration of the transition to the Hubble time. And in the standard literature, it is assumed that delta T electroweek is 1 Hubble time. From non-perturbative calculations that I'm going to come to in just a little bit, done by Guy Moore, what he found is that actually the duration of the transition is much shorter, about 1,000 times shorter. So that is something that one should have updated in this criteria. Remember the factor e to the minus n? Well, n tells us how big the initial baryon asymmetry is compared to what we need it to be. That defines the minimum washout factor, or the minimum washout factor. And so that number, it appears here as a logarithm. And in the standard analysis, it's assumed that the initial baryon asymmetry is e to the 10 times larger than what actually appears today. Realistically, n is order 0.1. So there's some update that comes to putting in a more realistic value of n. This 4 pi b over g, I already told you about. That is dependent on the particular model. And again, the Speyleron energy has to be recomputed in a different, in a new model. This is only known so far for the standard model in general. And then there are some other factors that are contained in this z times th, which I haven't told you about. But it all boils down to what we find is a much broader requirement, less stringent requirement on the ratio of V bar over TC due to the uncertainties in all of these factors, even in the standard model, to get us sufficiently large Speyleron energy. The ratio of V bar over TC could be somewhere between 0.4 and 1.4, okay? Whereas the standard requirement is that it's greater than 1, and it's not using this gauge invariant scale. So what about in beyond the standard model scenarios? All these things have to be revisited. What's the gauge invariant scale? How does the fluctuation determinant and the coefficient B vary with the parameters? In that theory, what is the initial baryon asymmetry? How long is the duration of the transition when you make it strongly first order with new fields? Now, let me again just remind you of some of these other terms. This first power of c comes from the exponential in the washout factor that I told you about before. The second comes from doing this careful integral over the zero modes associated with broken rotational translational invariance. Now, the standard procedure involves not ever working through all this explicitly, but taking the exponential part, taking some assumed values for all the other terms, and doing one more thing, replacing V bar of t by the value of the Higgs field that minimizes the full potential at a given temperature, and then using a gauge-dependent critical temperature. Not good. Don't do this. Do it the way that I've told you. All right, I'm running a little over time. I just realized that. I'm sorry. I got a little enthusiastic here, so I'll quickly say something about the non-perturbative calculation. This is done by Guy Moore, and this is a calculation that's now over 20 years old, and it really hasn't been updated. He uses a lattice calculation that is a real-time calculation and defines a quantity that defines different phases, a vacuum and a broken phase in field space called a separatrix. And he counts how many times in a random walk the field configurations cross this separatrix. And he uses that to define a rate. There's some details about the lattice that I'm not going to be able to tell you about. And then he does his own comparison with perturbation theory. There are a bunch of the quantities that we've been discussing. The important one for us is this gamma d over t to the 4. And in the top part of this table are the values obtained using perturbation theory in a particular gauge. I'm not sure this is even a gauge invariant calculation for the relevant logarithm of gamma over t to the 4. And the bottom gives the result of his non-perturbative calculation. And you can see that the rate differs by about a factor of 30. So that has some impact actually on the requirement on the washout factor, whether or not one uses a non-perturbative or a perturbative calculation. So really what one ought to be doing at the end of the day is going beyond perturbation theory to get a more realistic value of the Speyleron rate. But even if you do use perturbation theory, be careful that you do it in a way that is consistent with field theory, meaning gauge invariant, and takes into account all the ingredients that go into analyzing the baryon number preservation criteria. So let's just conclude with the key concepts from this lecture. Sphalerons are interesting, beautiful, and complicated and a little fraught, theoretically. So I tried to teach you how baryon number creation and washout work, the connection between sphalerons and topology, how to go about computing the sphaleron rate perturbatively in a careful way, and then I just finished with the state of the art about the comparison of the non-perturbative calculations. And that really is an open research problem, is to do that in beyond the standard model theories. Okay, so let's stop here and see if anyone has any questions from this lecture or the lectures on yesterday.
Thank you very much, Mike. Are there any questions from the audience?
I have a question.
Yes, go ahead.
It's a rather technical one regarding the fluctuation determinant you have just mentioned.
Mm-hmm.
So, is the fluctuation determinant is just the variance part of the settle point approximation when we do the path interval?
Yes.
So then what you've just mentioned is that, so basically, for making the settle point approximation, we only need to take the part which is quadratically approximatable, and that is the, so is that the point?
That's the point. In field theory in general, or even in quantum mechanics, you know that there is a quadratic correction, you know, to the saddle point solution, right? And so the subtlety for doing sphalerons is that the sphaleron configuration breaks the rotational and translational invariance that the vacuum maintains. And so you can't treat the modes associated with those broken symmetries as quadratic fluctuations. Everything else can, but you have to factor out those particular modes. And so it takes quite some care, and it's quite technical about how to do that. But it leads to some factors that you might not otherwise expect if you were to calculate the fluctuation determinant. Now, to calculate the fluctuation determinant is highly non-trivial, even after you factor out the zero modes. And that was done using a kind of a partial wave analysis in the Carson, Lee, McLaren, and Wang paper. And it really hasn't been done very extensively in beyond the standard model theories since then. People have tried to evaluate the saddle point, the leading order, classical configurations, and then have made the mistake of using gauge dependent quantities in that calculation. But then the fluctuation determinant is another challenge on top of that.
So the extension is not so trivial.
I'm sorry?
The extension to the calculation of the fluctuation determinant in the extended model is not so trivial.
Is not trivial. Is not trivial.
Okay.
So we don't really know what the impact of that is in beyond the standard model. All we know really is the standard model. Let me just show you this slide again. So lambda over g squared is the relevant quantity in that case. And here again is the exact calculation of McLaren and company. You can see that there's quite some variation with this particular parameter. So then what happens when we add more parameters to the fluctuation determinant? It's not clear.
Okay, thank you.
Thank you for the question.
Any other questions from the audience?
I have a question.
Yes, go ahead.
You said the temperature gauge dependent temperature. How can you avoid this problem?
So let me see. Yeah, let's go. Where did I? Let's go here. So in the paper here, 11014665, we discuss about using an H-bar expansion of the effective potential. And that allows one to respect something called the Nielsen identities. And so, that takes some discussion, which I didn't prepare slides for because it's very technical again. But, if you're really interested, I encourage you to read our paper and look at that. For some cases, for some theories, there are simpler ways to avoid gauge dependence. And again, that's a long, probably an hour-long discussion, actually. So there are strategies for avoiding gauge dependence in TC. For the energy of this aileron, again, you want to avoid gauge dependence by using this quantity I call V bar rather than the full field that minimizes the potential.
And you said that once we choose proper strategy, then we can avoid gauge dependency in energy and temperature.
Exactly. And the thing that, until we wrote this paper and struggled with it for a couple of years, we didn't realize is that for, a couple of decades or a decade and a half, people were using gauge dependent calculations to evaluate this washout factor. And in some sense, that became kind of assumed to be right. And so, we had to really do some work to think about what the strategy was. And it turns out this old calculation by Larry McLaren and collaborators did the right thing for East aileron. And then we pointed out you could marry that with a gauge invariant way of calculating the critical temperature. So I'm of course happy to talk about it, in the future for anyone who's interested. But there are strategies. One has to be really attentive to it.
Yeah, thank you.
Thank you.
Okay, thank you. I think there are a number of things that deserve more careful study, I guess. Okay, thank you. And let's have some break and meet again at 11 a.m. Thank you, Mike.
Sounds good. Thank you, everybody. See you soon. Let me stop the sharing.
Hello, everybody. Now, the Professor Ramsey Musolf will give the last lecture for this school. So please, Michael.
Right, everybody, welcome back. And so we're going to turn to the last topic. And let me start the slideshow. So the last lecture, I hope, alerted everyone to the fact that there are a lot of theoretical challenges associated associated with even just one piece of the baryogenesis, electroweak baryogenesis problem, which is this Phaleron rate calculation. And so I hope that may inspire some of you to think about those issues, and I'm certainly happy to discuss them you know, by email or Zoom later on after the school is over. So what I want to end with is maybe some what I call the electroweak baryogenesis theory frontier, which is really a set of other topics that also have theoretical challenges associated with them, which I think actually makes this field a very rich and interesting one because there's so much good quantum field theory to do. So let's look at what the goals are for this lecture. So as I said, I'm going to discuss several open theoretical challenges. One of them has to do with nucleation. And so I'm going to tell you about the standard nucleation or tunneling calculation. A second has to do with the validity of perturbation theory. And I'm going to share with you some recent results of non-perturbative calculations that help us understand a little bit just what are the limits of validity of perturbation theory, as well as discuss some of the in-principle reasons why you should be cautious in using perturbation theory in discussing phase transitions. And the third, following the question yesterday about the quantum transport for the CP violating part of the problem, I'm going to at least briefly introduce to you the transport equations for doing the calculation carefully. And hopefully all this material will inspire many, many more questions. So the three parts are nucleation, perturbation theory, and quantum transport. I've given you here a number of references for future reading on various aspects of these topics. And so I, again, encourage you to take a look at some of these papers and the references cited therein for more details. So let's start with nucleation. So the classic paper on nucleation or false vacuum decay is Coleman's paper in 1977. And I'm going to talk you through in a very sort of, I hope, clear and simple way what's already very clear and simple in this paper, but to try to give you the basic setup that people have been using for calculating the nucleation rate. So Coleman starts with a quantum mechanical problem about the motion of a particle in coordinate space. Q here denotes the different coordinates. And so this could be a multi-dimensional quantum mechanical problem. And there's a potential V. And the idea is to look at what's called the false vacuum in quantum mechanics, which is the point Q0, which corresponds in classical mechanics to a stable equilibrium position. Now, you know, of course, in quantum mechanics that there is no such thing as a stable equilibrium. The solution includes tunneling to the point sigma, at which point there is a probability of finding the particle anywhere here with non-zero kinetic energy. Okay. So the question is how to compute the rate to tunnel from Q0 to sigma. And again, think of these in multi-directions here. It's a one-dimensional plot, but it's multi-directions. So the rate is given in the formula on the right. Gamma goes like some prefactor A times an exponential that involves an energy over h bar, or units of, energy over h bar. Not energy, I'm sorry, action over h bar, my mistake. And then there are order h bar corrections to this formula that he doesn't worry about. The numerator of the exponential is b, which is an integral over the square root of twice the potential along a particular path. And the path is the one that minimizes this integral as we move from an initial false vacuum, denoted by the vector Q0, to the exit point in tunneling, where you head toward the true vacuum, and that is given by the point sigma. Now, it is convenient when studying this problem to work in imaginary time, as we did, by the way, earlier when we studied finite temperature field theory. So the identification is the following. The value of the coordinate in the distant past is going to be the starting point, which is the location of the false vacuum, q vector 0. And we'll take the 0 of time, imaginary time, tau, to be the time when we land at the point sigma. And the time derivative, the imaginary time derivative at each point has to be equal to 0. So we solve for the path that minimizes b in imaginary time subject to these conditions. Now, it turns out that one can show that, in fact, with these conditions, that we're at 0 of energy, that we go from Q0 to sigma, and with the boundary conditions as given, then this integral for B is actually the integral over imaginary time of the Euclidean Lagrangians. In other words, it's the Euclidean effective action, where we integrate from tau minus infinity to plus infinity. So the path S that one follows is actually the path that minimizes the Euclidean action. And that leads to a set of equations, which are maybe not surprising. Second derivative of Q with respect to tau is equal to the gradient of the potential. And that's the equation we have to solve subject to the boundary conditions to then compute B. And what it looks like, in fact, is the equation for a classical path, but in an inverted potential, because in a classical mechanics, the right-hand side would be minus the gradient of the potential. So it's as if we solve the classical equations of motion, where the time variable is tau, for a potential that is actually minus the potential that we're interested in. Okay? So that's sort of a nice observation. And so now we start this solution at the initial point Q0 in minus infinity, and the solution is one that takes us at time to sigma rather at time 0. And as Coleman points out, it is symmetric in the sense that the evolution from time goes from 0 to plus infinity takes one back to the point Q0. So it's as if you start at Q0, you roll down this potential up to sigma, and then you bounce back down and roll up to Q0. Hence the name bounce solution. Okay? And that's, I think, his terminology, bounce solution. So that's quantum mechanics. What about field theory? Well, in field theory, we have an analogous problem. Here is now the inverted potential. And the idea is that if the distant past in imaginary time or the distant future, we would be living in the false vacuum. And the question we want to answer is, what's the probability that we exit the false vacuum to the region of the true vacuum? And so that is going to be solved in an analogous way to having solved the decay of this false vacuum point to the exit point into the region of the true vacuum. Now we're going to do it field theoretically, and the potential is U. So we start at minus infinity at the false vacuum. The field configuration is phi plus. And somewhere over in the left-hand side is the exit point. It's not exactly phi 1 for reasons we'll see later, but somewhere in that vicinity is the analog of the exit point we called sigma previously. The exponent in the rate for the transition is the Euclidean action. So here it is. So we're using imaginary time. The potential, again, we're calling U instead of V. And what Coleman does is he says, let's make the assumption that there is rotational symmetry in space. And so everything can be thought of as just a function in four-dimensional space-time, rather Euclidean space, as just a function of tau and the magnitude of x. And we'll define a corresponding 404 or four-dimensional Euclidean radius variable rho in the following way. So we now ask, what is the path to go from phi plus to some sigma that minimizes the Euclidean action? And that leads to the following equation of motion for phi. Okay, d squared phi by d rho squared plus 3 over rho d phi by d rho is equal to the gradient of u with respect to phi. And that looks a lot like the quantum mechanical example, except for one thing. And the one thing is this second term on the left-hand side, which looks like a friction term, something that is proportional to the gradient of phi with respect to the rho variable. What that means is that the exit point can't be phi 1. Because let's imagine that we start here, and instead of evolving according to simply minus to the gradient of u, there is a friction term that's slowing down the field. And so it can't make it all the way up. Or conversely, if we started at time 0 at phi 1, the phi field would not have enough energy to make it back up to phi plus because of this friction term in the equation. So the appropriate matching point where the exit solution comes has to be a little bit higher on this potential on the left-hand side than it would have been in the simple quantum mechanical case. So how do we find that value of the field, the analog of sigma? Well, it's possible that it might be at phi minus, but what Coleman shows is that if you were to start at phi minus, then you would roll down, you would roll up, and then you would go past phi plus. That's called overshooting. If you start at phi 1, as we said, you wouldn't make it all the way back up. So that's undershooting. So the method is to try various values of the exit point between phi minus and phi 1 until you find one where you exactly roll down and end at phi plus and then roll back and end at that exit point. It's called the overshoot undershoot method. And it's been kind of a standard procedure in the literature for finding these solutions, the bounce solutions. Okay. Now, what about at finite temperature? What do we do? Well, at finite temperature, we're not interested in tunneling as the time dependent because we're analyzing the potential in imaginary time already, where imaginary time is equal to 1 over the temperature. So the problem we have to analyze instead is in the space of 3-dimensional coordinates, just ordinary R3, what are the solutions for phi in the presence of the finite temperature effective potential? So now on the vertical axis, I have minus v of phi and t, and instead of using rho, we're going to use r. So the tunneling rate is then going to be given by a prefactor e to the minus beta, the 3-dimensional effective action, which is given in the box on the lower left. There's no time variable anymore, no imaginary time, because we've turned that into temperature at finite temperature. But everything else looks the same. So we want to find the path from phi plus to sigma that somehow minimizes SE, and that leads to the following equation for phi as a function of r. And there's a friction term. It's a little different than the one we had before. It's 2 over r rather than 3 over rho. And on the right-hand side is the gradient of the effective potential with respect to temperature. And by the way, the prefactor has been found to be some order 1 number times temperature to the 4th power. Now, you can already see that some of the ambiguities that we have already been discussing with regard to other calculations at finite temperature field theory will propagate into this problem. because the effective potential in general has a dependence on the gauge parameter. So naively, even in the standard model, you would obtain a gauge-dependent result if you weren't careful. And that turns out to be one of the challenges in this business. But we'll come back to that in a minute. Well, let's assume we can obtain a well-defined value of phi. And remember, it requires having a barrier between the false vacuum, this symmetric phase, and this would be then the broken phase in the electroweak theory where I've turned the potential over. What's the requirement on the parameters of the theory so that you actually make this transition out of the false vacuum? Well, the requirement is that at least one bubble, one solution can happen within a horizon volume at that temperature. So how do we analyze that? Well, we go back to our second lecture, the Friedmann equation, and where we worked out that in the radiation-dominated era, the time goes like 1 over the temperature squared, and of course there is dimensionally, there has to be a mass in the numerator, it's the Planck mass, and the coefficient, which we didn't derive then, is actually given by a very simple formula in the box over on the right. It involves just numerical factors and then the total number of relativistic degrees of freedom. In the standard model, that number is a little less than 107. So then the volume, it turns out, is just to take twice the temperature and scale it, of course, to get a length unit and cube it. So we get this formula in the middle box. So we have to be able to nucleate one bubble within this horizon volume in order for the actual phase transition to occur. So what is the probability to nucleate one bubble? Well, the probability is given by the rate, which involves this exponential, and it involves an order 1 number times t to the 4th times the volume, and then the time derivative. It turns out when you put this all together, the time differential gives us dt over t in this formula. And we have to integrate that from the beginning of the nucleation process, which is a temperature just a little bit below Tc, until infinite time. That's the total probability to nucleate one bubble within the horizon volume, because that rate that I gave you, and I didn't say this before, that rate is actually the rate per unit volume. And that has to be at least order 1. And it turns out that imposes a requirement on the value of the 3-dimensional effective action. And that requirement is that at the nucleation temperature, S3 over T nucleation has to be less than something like about 135. Otherwise, we are not going to nucleate quickly enough to make one bubble happen within our horizon.
Here I have a question.
Yes.
Shouldn't the vector inside the integral be 2 zeta mt over t squared? Because
No. But remember, there's a t to the 4th in the rate. There's an order 1 factor times, let's go back here. The prefactor is a t to the 4th.
So they got merged.
Yep.
All right, thank you.
Yep. So I actually checked this formula. You can find it in the KIAS article, but I checked it, so I think it's correct. So other questions before I go on? All right. So this is a requirement that if you're analyzing phase transitions, not only do you have to get a first order phase transition, but you have to demonstrate that the transition will actually complete by nucleating at least one bubble within the horizon volume. And that means that you have to compute the 3-dimensional Euclidean action at the nucleation temperature and compare it to the nucleation temperature and see if this requirement is satisfied. And oftentimes people will use the critical temperature to do this evaluation. And it's a pretty good approximation, but rigorously speaking, you should use the nucleation temperature. So there are a number of theoretical issues associated with this. This is the standard setup, and I've just listed some of them here for you because each one of them would require an hour-long lecture, or at least part of it. The first is, in many theories, like the standard model, the barrier between the false vacuum and the true vacuum is induced by thermal loops. It's radiatively induced. And as we already saw, the effective potential, the cubic term that gives us the barrier, is gauge dependent. So how do we handle this problem? Well, it's been shown how to do that at zero temperature in this nice paper by Weinberg and Metaxas, and also a later paper by Matt Schwartz and his students and postdocs, how to do it in the standard model. But at finite temperature, it seems to be an open problem about how to do this when you have a radiatively induced barrier. A second problem, which still has the gauge invariance issue as part of it, is how to handle a situation where you have multiple fields. Solving the bounce for the bounce solution becomes really complicated in the multi-field space. So several years ago, a former UC Santa Cruz student had worked out code for doing that, not using the bounce procedure. It's called Cosmo transitions, and it is now widely used in the community to find the tunneling solutions. But again, you have to be a little bit careful, actually a lot bit careful, when you use Cosmo transitions to ensure that the solution you get is gauge invariant. More recently, there's been some work by Jose Ramon Espinoza on an alternate method, and it's a very clever idea, and it's still under scrutiny about whether it can satisfy the requirements of gauge invariance, and that's something that I'd be happy to talk to people about later, but it's a more recent development and certainly very interesting. So just to let you know, there are challenges in doing this part of the calculation. Now, one of the places where it actually is quite relevant is not just for analyzing whether or not we have a first order phase transition, but actually computing gravitational waves that come when the bubbles expand and collide. And I'm not going to be able to, I don't have time to tell you about how to do the calculations, but I'm just going to highlight for you what the pieces of physics are. So you have these bubbles that expand and they collide, and there's all kinds of stuff that goes on. There are detonations, there's violence at the collision fronts. There's turbulence and damping. And then after the bubbles collide, it has recently been realized that there are sound waves that propagate in the plasma that last a rather long time. And those sound waves actually can be the dominant source of producing gravitational radiation. If we had more time, I would show you now, but there's a nice sort of visualization of this that my colleague David Weir and his collaborators have put together. And here's the link if you want to go look at it. It's really kind of pretty, but I don't think we have time to do that now. So you also are probably aware that there are future gravity wave experiments that are very interesting, and in particular, the LISA experiment that is planned by the European Space Agency will start to have some sensitivity to the gravity waves that would be produced by an electroweak phase transition. And we'll come back in a minute to see just how comprehensive its sensitivity is. There's also, by the way, some efforts in China similarly, but so it's a very hot topic. But it requires doing these calculations in a way that is careful, okay? So what goes into the gravity waves? Just very briefly, the two ingredients. One is the so-called normalized latent heat. The latent heat is defined in terms of the change in the free energy and the temperature times the change in the entropy. If the free energy is approximately equal to the potential, then we can compute everything here by calculating the effective potential. Okay, so delta Q is given in terms of the change of the effective potential and the temperature times its derivative with respect to temperature. And so the normalized latent heat, the quantity that people actually use when they discuss the strength of gravity wave signals, is alpha, which is a ratio of delta Q over T to the fourth. So it's delta Q is per volume. And so this has the right units, and then there's some numerical prefactors. So that's one quantity that one uses in gravity wave calculations. The other is a normalized time scale that can be expressed in terms of the logarithmic derivative with respect to temperature of this ratio that goes into the numerator of the exponential factor, S3 over T. And it is normalized to the Hubble parameter at a particular Hubble rate at a particular time. And that's an important ingredient for telling us about the frequency of the gravity waves. So one of the open questions that one should ask is, when we do these calculations, how reliably can we calculate delta Q and beta over H star? Which brings me to my next topic, which is the reliability of perturbation theory. So I've thought about this, in terms of the following, that we have theory of how to do these calculations, the quantum field theory, and then we have the phenomenology and the model building. We want to take models and we want to ask whether they generate the baryonic symmetry, what are the experimental consequences in collider physics, electric dipole moment searches, and gravity wave searches. And so how are we going to make sure that the theory is as robust as possible when we try to do the phenomenology and the model building? So there are two sides of this. There's the right way to do the calculations, which is non-perturbative. The downside of that is that it's really hard to do a lot of survey of different models and parameter space using non-perturbative calculations, because they're numerically intensive and they take a long time. And so you can't just scan over lots and lots of parameters and lots of models as you can in perturbation theory. So perturbation theory allows you to do that and to make predictions for experiment, but it really raises questions about its reliability for reasons that we will discuss. So the forefront here is really to try to benchmark perturbation theory by doing a sufficient number of non-perturbative calculations of various quantities in different models to assess, how close are the perturbative calculations that we use to analyze broader regions of parameter space. So why would you worry about perturbation theory? Well, there's a couple ways to look at it. The first is a classic problem known as the Linde problem, and here's the reference to Linde's paper. And the idea here is the following. It has to do with infrared behavior of field theory, gauge theory at finite temperature. And the starting point is to look at the finite temperature inverse propagator for Yang-Mills theory, and here it is for the massless Yang-Mills theory. So this might be QCD, for example. And the general expression for the inverse propagator at zero frequency and finite momentum and temperature is on the right-hand side. There's a k-squared term, there's a k term that is proportional to g squared t, there's a k independent term, et cetera, et cetera. It turns out that for sufficiently small k, this series diverges. And so you have to cut the theory off at an infrared cutoff. And that infrared cutoff is g squared times the temperature. In other words, don't believe it perturbatively below that scale. So that's point one. Point two is, what happens to quantities that we might actually calculate using these propagators? Okay. The example that Linde uses is something called the thermodynamic potential. And as you may remember from your graduate student course, the thermodynamic potential is the chemical potential times the total number of particles. That can be computed in massless Yang-Mills at order n in perturbation theory. So n is the loop order, and it depends on temperature. There's an overall factor of g to the 6, t to the 4, and then there is a quantity that depends on the ratio of g squared t to the infrared cutoff. And it's raised to this power, n minus 3, where n is the number of loops. So for anything greater than n equals to 3, every contribution is going to be of the same magnitude. So there's no truncation of the perturbation series. Perturbation theory breaks down. Okay, so one finds in calculating quantities at finite temperature at sufficiently high loop order infrared problems that start to come in and plague your perturbation theory. So that's a reason number one to worry. Another example would be in something like the standard model where you have spontaneous breaking of the symmetry due to the background field. It turns out at finite temperature, the effective parameter that enters the perturbation theory is a ratio of a three-dimensional gauge coupling, G3 squared, divided by the field-dependent finite temperature mass. So that number in the vicinity of an electroweak phase transition in the standard model for a light Higgs, so 70 GeV Higgs, where the critical point for the phase transition in the standard model occurs, that number is not small. So there's really no small expansion parameter that one can use. So you should worry about how well perturbation theory guides us. And that leads to this program of trying to benchmark perturbation theory using lattice calculations. And the most sort of efficient and systematic way to proceed these days is to start by working with something called dimensionally reduced three-dimensional high temperature effective field theory, which it turns out is a way to systematically carry out the thermal resummations that we talked about when we discussed the daisy resummation. Once we have that dimensionally reduced high temperature effective field theory, that is much more straightforward to simulate on the lattice than the full theory. And so for other reasons, we'll see why this is also advantageous. But I'm going to now tell you in broad brushstrokes, what is this effective field theory approach? It's really encoded in this diagram here. The vertical axis corresponds to different mass scales in finite temperature theory. Up at the top are the mass scales associated with the non-zero Matsubara modes. Remember the Matsubara modes go like pi times temperature times an integer n. And so we're going to call those the super heavy scale. A little lower down, instead of pi times t, there is the gauge coupling times t. We're going to call that the heavy scale. And then the scale associated with the infrared behavior, g squared t, we're going to call the light scale. So the way the three-dimensional high temperature effective field theory works is we start with our full theory, let's say the standard model, and we do all the integrals at, say, one loop order, but only carry out the integrals involving the non-zero Matsubara modes. That leads to a three-dimensional effective field theory. It turns out that if we integrate out the zero component of the gauge field, that can have a mass that is order g times t. So that's called a heavy mode. When we integrate that out, we're left with a final theory that only involves the light degrees of freedom. And we call that L bar 3. So this has been used extensively in the early days, in the 1990s and beyond, for the standard model and the SU2 left Higgs first in the standard model. And as I said, it was a way to carry out a systematic resummation of those thermal effects. And it leaves us with a theory that can be used for lattice calculations straightforwardly. And so in the standard model, the potential is really simple. It involves a quadratic term and a quartic term for the Higgs. There is a temperature-dependent three-dimensional mass squared and a temperature-dependent three-dimensional quartic coupling. And those numbers are obtained by following this procedure that I've outlined here. Lattice simulations have been done for this theory. So what about beyond the standard model? How are we going to assess perturbation theory for beyond the standard model? Well, the idea here is to what we call repurpose the existing lattice results for the the three-dimensional, dimensionally reduced effective field theory. Here's how it works. In addition to the non-zero Matsubar modes, we can assume the beyond the standard model fields are heavy or super heavy, and we integrate them out. Okay, so that's the first upper part of this. So in our procedure, we include those contributions to the integrals that then will leave us with parameters in the low energy effective theory that are functions of the parameters associated with the new fields, the beyond the standard model parameters. Then we can use the existing lattice calculations to learn where in the space of mu bar and lambda 3 one has a first order electroweak phase transition, and infer back to what the parameters in the full theory had to be in order to make that happen. So let me illustrate some results that recently have been obtained using this procedure. And I'm going to do it with two very simple Higgs portal models. One involves adding just a gauge singlet scalar to the standard model, and the other an electroweak triplet. And I'm actually going to start with the electroweak triplet. And so if we go back to what we discussed yesterday about the classification of the patterns of symmetry breaking in the early universe, we can think about what the triplet, real triplet, might do. And by the way, the real triplet carries no QCD quantum numbers. It's a triplet under SU2 and has no hypercharge. And the neutral component is the phi field in our diagrams here. It turns out that in this particular model realization, both of these h squared phi squared effects can lead to a first order phase transition. The first one, we've been able to analyze rigorously using this repurposing of lattice results. And the second one, we actually have a recent result for an explicit calculation where we haven't integrated out the real triplet. But I want to first show you the result of doing the dimensional reduction where we assume that the triplet field is super heavy. Here's the phase diagram. On the vertical axis is the Higgs portal coupling, this A2 parameter. On the horizontal axis is the mass of the triplet. The gray region we can't access using this dimensional reduction procedure where we integrate out the triplet because the triplet is too light in this region here. But we can access the colored region. The green corresponds to the region in the space of A2 and M where we would get a first order phase transition. So back to this slide here where this transition is first order. The blue corresponds to the region where it is a crossover transition. And I just want to emphasize that we cannot determine using perturbation theory where a crossover transition occurs. It is only something that we can learn about from non-perturbative methods. So the boundary between, in parameter space, between a first order transition, this would be the sort of the critical line, and a crossover region is only something we can obtain using these lattice methods in this effective field theory matching. Now there's a very interesting use of this for phenomenology, and this is now where more rigorous theory meets experiment. These lines, dotted lines, correspond to relative shifts in the rate for the Higgs to decay to 2 photons. Remember I discussed yesterday, one of the ways these h squared, phi squared interactions can show up experimentally is that if phi is a member of an electroweak multiplet, the charged particles can live in loops that affect the Higgs diphoton decay rate. The coupling here is the Higgs portal coupling, and it's dependent then on the coupling and the mass, and that gives you these dotted lines here. Let's imagine that experimentally we could learn something about the mass. The way to do that is to use something called the disappearing charge track. That's a technical point that we won't discuss. But if we learn something about the Higgs diphoton decay rate, then we could use the mass information and this dotted line to tell us whether or not we live in the blue region or in the green region. In other words, experiment can be a probe of the phase diagram. which I think is really cool. Now, as I said, let's see, why is this here? I want to now talk about this gray region because there are new results here, which actually include the lattice as a real explicit field in the lattice calculation, use the triplet in the lattice calculation. Here's the same phase diagram where now the little sliver of space here corresponds to this second phase transition scenario where we first go to the triplet phase and then to the Higgs phase. And the crosses correspond to actual lattice simulation results that validate that one can have a two-step phase transition. And for some regions, it's all first order, the light blue. And in this orange region, the first transition is a crossover and the second transition to the Higgs phase is first order. So again, that's all interesting information that we learned from the lattice once we have carried out this effective field theory procedure deriving the low energy effective field theory. Let me do another example, gauge singlet. I'm not gonna go through a lot of the details in this because I think you probably got the idea and I want to spend a little time on the CP violation. In the gauge singlet case, all three histories are possible. So there's an A2 term and an A1 term. The same kind of phase diagram emerges and it has interesting phenomenology, and I think I won't belabor that point here. But what I wanted to do with this example was to make connection with gravity waves. So the way, again, the gravity wave calculations are done involve these two quantities, the latent heat and this beta over H star. And in this plane, one can work out what are the sensitivities of the LISA experiment, the so-called signal to noise ratio curves. The sort of the minimal sensitivity is this one here. This is signal to noise order 1. Anything beyond that, LISA really couldn't see. Over here, LISA has quite a bit of sensitivity. The three-dimensional standard model-like effective field theory, actually in the case of both the triplet and the singlet, lives in this purple region here. So you can see that when the new scalars are sufficiently heavy, the transition can still be first order and generate gravity waves, but not at a signal large enough to be seen in the next generation gravity wave experiments. And we now know this from non-perturbative studies. It would take lighter degrees of freedom to get us closer to the LISA signal to noise. A point that I meant to make here, I don't know why it somehow disappeared, is that the collider experiments are still nonetheless able to probe this purple region. So even though the next generation gravity wave experiments might not see it, you would still get circumstantial evidence for indirect evidence from the next generation, the collider experiments. So one last slide on benchmarking perturbation theory from the same paper, which is comparing different quantities that one gets that are relevant to the gravity wave calculation, the nucleation calculation from the lattice and from perturbation theory. The non-perturbative results are in the first line. Four-dimensional perturbation theory, the way people do phenomenology is given in the bottom line. You can see that for the latent heat, there is a rather dramatic difference, factor of 2.5. For beta over H star, there's also quite a significant difference. And even if you would do a better job with the three-dimensional effective field theory to calculate beta over H star, you're still, you know, something like 25% wrong compared to the non-perturbative results. So it really emphasizes the importance of assessing the reliability of perturbation theory with non-perturbative calculations. The same thing has to be done for the other processes of interest and quantities of interest for baryogenesis. The Sphaleron rate we already discussed, the nucleation rate we already discussed. Something we didn't discuss at all is those bubbles, they have velocity of expansion and they have profiles, and both of those aspects of the bubbles are important for how effectively you can actually generate a baryonic symmetry and generate gravity waves. And those calculations also are being improved, but really require further thought. Okay, so the takeaway message is there's lots of room for really talented early career theoretical physicists to get involved in this stuff. Let me conclude with just a few minutes on the quantum transport for the CP violation part, because a question was asked yesterday. I added some slides a little more extensively just to show you what the ingredients are. And the problem, as you may remember I mentioned yesterday, is that to calculate the actual asymmetry that results through the interactions at the bubble wall, we have to deal with the fact that particles are propagating in the background of the changing Higgs field, and that's changing their masses. So masses then are becoming a function of space-time, okay? So when the particle's coming in, it doesn't just see a sharp wall, it actually sees some profile in space. And so as the particles are coming in, it's starting to change its mass because the Higgs field is turning on and its mass is changing. So this is a non-trivial problem to do carefully. And so let me just tell you how we set up to start to address it, a little bit what some of the progress is and some of the open questions. So the formalism for doing this is something called closed time path formulation of quantum field theory, or Schwinger-Keldysh formulation. And in this setup, there are a more complicated set of Green's functions that one has to include in any calculation than one does in ordinary equilibrium quantum field theory. And the Green's functions are listed in a matrix here. For a scalar field, the upper left is the ordinary time-ordered product of vacuum expectation value of time-ordered product. But there's also an anti-time ordered Green's function. And then there are two other Green's functions that are called the Whiteman functions that one has to include. And it turns out that the calculation using this full set of Green's function is the only appropriate way to deal with thermally averaged or so-called in matrix elements of field operator products. They contain the full information on number densities, and this formalism can be generalized to a multi-flavor problem. I've just done it for a single flavor here. And here are a set of papers for which I've been, on some of them, a co-author that talk about this. So if you want sort of a pedagogical introduction, I would encourage you to take a look at these papers here. So to solve the Green's function means you really have to solve a Schwinger-Dyson equation, which is given symbolically in the bottom here. So G tilde is the free Green's function, G tilde with a zero is the free Green's function, G tilde without the zero is the full Green's function, sigma tilde is the self-energy, and the tilde means the full matrix of all these Green's functions. Now, in practice, the best way to solve this, well, it turns out to make progress, we have to exploit scale hierarchies that exist in the problems. And I think given the time, I'm not going to belabor that point, but I just wanted to give you a flavor for what the formalism looks like. What we actually do is go to what's called Wigner space. A Wigner transformation does a Fourier transform in the relative coordinate, but keeps the dependence on the average coordinate. So remember, we have Green's functions where we have two coordinates. So the Wigner transformation is the Fourier transform in the difference of x and y, and capital X is the average of x and y. So it turns out to be more convenient to work with these Wigner transformed Green's functions. And for one of the Whiteman functions, there's a corresponding what's called kinetic equation that involves a dot product of the momentum and the gradient with respect to the average coordinate and a bunch of terms on the right-hand side. So what are the terms on the right-hand side? Well, the important one for us involves this mass squared matrix. In general, the mass is changing as a function of space-time. And so that means that to get the mass eigenstate, we have to redefine the field at every point in space. And so the operator that does that, I'll call U, and the mass matrix that gets redefined is then given by this U dagger, the unredefined mass matrix here, U, and it turns out that in the Lagrangian, the result of introducing this redefinition of the fields is to introduce a new field called sigma. Sigma involves U dagger and its derivative. So this mass squared commutator with the Green's function, if it involves more than one flavor, leads to flavor oscillations like you would get in neutrino oscillations. But the important point is this second term that involves the dot product of momentum and this sigma function, yeah, which comes from redefining the field at every point in space. And that is the source of CP violation. So the kind of the crux of this problem has been to carefully evaluate the CP violating source. And there's been some progress, but there's been a lot of controversy about it. So just to alert you to the fact that this is an interesting and open problem, but I think for the scalar field case, we pretty much know how to solve it. As I'll say in a minute, the fermion case is still an open problem. The last term, by the way, is our friend the collision term, written in a slightly different way, that as we saw in the case of leptogenesis involves all the scattering, the decays, the thermal masses, and all these particle species changing reactions that can happen in the plasma around the bubble. So to solve for the baryon asymmetry, we really have to set up this full set of these kinetic equations for the Wigner space Green's functions, solve them, and from that we can derive the actual particle number densities. Okay. Open challenges include applications to realistic models now for scaled field theories, and the full formulation for fermions is still a work in progress. So let me conclude. The key takeaways from this lecture. I didn't actually put my right concluding slide here. I'm sorry. So I will send an updated version of this one. I copied the key concept slide. The key takeaway message is that there are lots of open theoretical challenges. Let me just put it that way. Perturbation theory needs to be assessed. Doing perturbation theory rigorously, is not always been the case, and that has to be done. And for the quantum transport, there are even open sort of formulation problems that are still out there for someone to tackle. So let me stop. We've done 8 hours. I hope I've given you a good sort of first overview of the context for the baryogenesis problem, some of the main scenarios that people are thinking about in particle physics to try to address it, the various theoretical tools that have been developed to try to calculate the baryon asymmetry and apply to experimental tests, as well as the open challenges that really call for involvement of more people. And so I again put down my contact information here in case anyone is interested in following up. And with that, I will end these lectures. So thank you very much.
Thank you very much, Michael, for this nice comprehensive overview of the topics. Any questions from the audience?
I have one question about the current status for the application of the the lost topic for scalar field theories.
Mm-hmm.
So there if I remember correctly, I think I heard you saying that we now have quite a comprehensive understanding about the application for the scalar field theory, while we don't really have a full formulation for fermion cases. Then why is the application to real scalar field theory an issue about this?
Well, it's not so much an issue. It's just that the papers where the formulation was done used toy models, but not realistic baryogenesis models. So what one would now like to do is to go to